I think we will continue on moment generating function. Is that correct? Yes.
Yes, ma'am.
Okay. So as a review, your covariance of your random vector y is always non-negative definite matrix, no? But if your y has a continuous density function, then the covariance matrix of your y is positive definite. Now, it is very important for a matrix to be positive definite because sa ganito akong gisulti. Gano importante na positive definite? Okay, we denote a positive definite matrix in this symbol. Nganong gani? Anong gusto nato? Positive definite? Anybody?
Ano siya, ma'am? Para unique. May invertible siya, ma'am.
Okay, a positive definite is the inverse will exist, no? It's invertible, so the inverse will exist. We want that because we usually want x prime x in our estimate, and that x prime s inverse should exist in the computation of our estimate later in linear model. So now, that was Shera. Isa to ni Tingog. Isa to ni Tingog.
Hello, ma'am. Ako, ma'am. Shara, ma'am.
Shera, okay, very good. Okay, so let's now have the definition of a moment generating function. Okay. So here we have a vector t. This vector t follows whatever is the dimension of your y. So if your y is an n by 1 random vector, your vector t is also an n by 1 vector. So we have a vector t and you have your usual vector y. So this is transpose. So ibig sabihin, your y is written in this manner as well as your t, no? So these are random vectors. Then the moment generating function of y denoted by this symbol my at t. My of t is the expectation of the exponential of the summation of yi ti, I from 1 to 10, n, or equivalently, you can write it in this manner. Expectation of e to the y prime t. So e to the y prime t is actually y1, y2, to yn, and then your t is t1, t2, to tn. So that what you have here is y1 t1 plus y2 t2 plus so on so forth plus yn tn, or equivalently that is your summation of yi ti, no? So that's why this notation is equivalent to this notation. So memorize this, that the moment generating function is the expectation of e to the y prime t, provided that that expectation exists for every t in the neighborhood of t between negative h and h, where h here are some positive number. Okay. Lemma 1.23 says that if you have two random vectors that have the same moment generating function on some open set containing the origin, then they have the same distribution. So kung si x will have a moment generating function say x, and si y manpareha sila, ang moment generating function of y is just equal to the moment generating function of x, then this will imply that x and y will have the same distribution, no? So ibig sabihin, kung ang moment generating function ni x, ang itsura niya normal, and then ang moment generating function ni y, parehag itsura sa moment generating function of x, say normal, so ibig sabihin x and y the same distribution, or both of them are normally distributed. So what is this lemma telling us? This lemma is telling us that moment generating functions for random vectors are unique. So kung pareha silang itsura sa moment generating function, ibig sabihin pareha sila og distribution. So unique ang mga moment generating functions for the different distributions. So if you have a normal distribution, ang moment generating function sa normal, lahi kung ang imuhang random vector is binomially distributed. So lahi ang moment generating function sa binomial. Okay, the next lemma, 3.4 in Arnold. So you have, okay, this should be prime. You have a y, n by 1 vector or random variables. Then we let x. So kung naa kay y, so si y na ay kaugalingon moment generating function sa y. Okay? So si y na ay moment generating function. Let us call it m, y at t. And then you do some transformation on y. Ang imong transformation gihimo is x is equal to ay plus b. Then gusto nimo pangitaon unsa naman karon ang moment generating function sa x. Kung si x is ay plus b. According to this lemma, the moment generating function of x will be equal to the moment generating function ni y at a prime t. So, punani mo a prime before t. So, moment generating function ni y at a prime t times this constant e to the b prime t. So, kini siya, diha na siya paingon, and then si a may mong a prime. Okay? So, to prove that, okay, by definition, in general, the moment generating function of any random variable w is the expectation of e to the w prime t. That is by definition. That is the usual definition of our moment generating function. So the moment generating function of x is the expectation of the exponential of x prime t, that is by definition of moment generating function. And then how x is defined, x is equal to ay plus b. So x will be ay plus b prime t. And then if you apply the prime, okay, again, if you have a, so if you have x plus y prime, and this is equal to x prime plus y prime, so linearity of transpose. And if you have ab prime, and that is equal to b prime a prime. So applying the primes here, so what you will have is, and distributing t to each of the terms. So you have the prime of a y is y prime a prime times t, and we have b prime t. Okay? So up to that line, that is okay. And then e to the a plus b is actually can be written as e to the a times e to the b, correct? So this is what happened in the next line here, that the exponential of y prime a prime t plus b prime t will just be equal to the product of e to the y prime a prime t times e to the b prime t, but the expectation of a constant times any random variable is just equal to the constant times the expectation of x, so that this is a constant with respect to expectation. You can put it outside. So what remains is the expectation of the exponential of y prime a prime t. But by definition of moment generating function, if you look at this, if you have a w there, that is just w prime here. So what we have here is you have a y prime here. So that will be the moment generating of y at a prime t. Okay? So mao ni ang mugawas, mura siyang expectation of e to the y prime and then that. But that is the moment generating of y at that. Okay? Any question? This is clear? Is this clear? Class? Are you still there?
Yep, ma'am.
Do you understand? Wa mo ni maningog akong estudyante. Do you still hear me?
Yes, ma'am. Yes, ma'am.
Thumbs up pud mo oy or unsa ba? Or magway tao then
Yes,
hey.
ma'am.
Okay. Next, another transformation that we are going to do on y is we have a scalar c and we transform y into z, which is the product of c times y. So again, your y has a moment generating function denoted by my at t. You transform y into z, and we want to know what will be the moment generating function of z. According to this lemma, the moment generating function of z is just the same as the moment generating function of y, but this time at ct. Okay, so remember again, the general formula of a moment generating function is the expectation of e raised to the w prime t. So the first step here is just by definition of your moment generating function. The second step here is just substituting your z by cy. The third step here is finding the prime. So this is expectation of e, y prime, c prime, and then t. But then again, c prime is just equal to c since that is just a constant. So you can write this as y prime ct. But by definition, again, of moment generating function, this is the moment generating function of y at this term, ct. So we have shown that the moment generating function of z at t is just equal to the moment generating function of y at ct. Next. Suppose we partition your y. So again, your y is from y1, y2 to yn. Suppose we will partition it. So the y1, y2 here is not just two variables. It can be a matrix, a vector within. So pwede nato ibutang na we can subdivide it as y1, y2 to yp. And then yp plus 1 to yn. No? So pwede kini siya will be your y2. So this is abuse of notation and this one will be y1. Are you following? So ibig sabihin, we are partitioning the vector into two. So the y1, y2 here is an abuse of notation. It doesn't mean that you just take the first two element of your vector, but you can partition it into two vectors. The same thing, similarly of how you partitioned your y here, suppose we can partition also yt1 and t1 and t2. So the purpose of this is for us to take the marginal moment generating function. So what will be the moment generating function at y1 and what will be the moment generating function at y2? So again, I want to emphasize that this y1, y2 here is not necessarily the first two element in your y, but it is a partitioning of your vector y. Do you understand?
Yes, ma'am. Yes, ma'am.
Okay. So for the proof, if we partition our y, say for example, y1, y2, y3, so on and so forth to yp, and then yp plus 1 to yn, no? So you can partition it in this manner that you can call this as y1, y2. But your y1 is actually the vector y1 to yp, and your y2 is the vector from yp plus 1 to yn. Similarly for t. So, kung kinira ang gusto nimo na vector unsay moment generating function ana, according to this proof, it is equal to the moment generating function of the original y, where the next compartment there or the next partition there is 0, and for y2 din he 0, no? So recall that you can write if you have a w, the moment generating function of w is equal to the expectation of e to the w prime t, but in terms of summation, that is the expectation of exp times the summation of w I ti, di ba? So it means that this one can be written as the summation of y1 prime t1 plus y2 prime, wherein kini siya, summation na siya ha, mga summation sa y2, but the t's are 0, and this one are summations of y1i, t1i, no? I from 1 to p in our notation. So this term here can be written in terms of summations. So in notations, you have this one. But this is just the moment generating function of y when these terms here are just 0. Okay? You can do the same notations there for y2. So this is actually marginals of partitions of vectors, the moment generating function of the marginals. Okay. Now, if your partitions of y here, y1, and here is y2 are, if these two vectors here are independent, this is if and only if the moment generating function of y can be expressed as the product of the moment generating functions of the marginals. But since this is if and only if, ibig sabihin, if you can express the moment generating functions of the marginals or the partitions into product, then we say that y1 and y2 are independent. So since this is an if and only if statement, so if and only if statement, P if and only if Q. So you have to prove first that P, so assume P and show it is Q. And second, you assume Q and show it is P. That is the usual way of proving if and only if statements. So for P implies Q scenario, so you suppose that y1 and y2 are independent. Then by definition of moment generating function, the moment generating function of y at t, but your t is expressed in this manner, can be written in this as the expectation of E. So again, recall if you have a W, the moment generating function of your W is equal to the expectation of E to the W prime T, or equivalently, you can write it as the exponential of the summation of WITI I from 1 to n. So similarly, you can write it as the summation of y. Okay? So actually, kini summation na siya sa y1i ti, t1i, I from 1 to p, and this is also a summations. And then, again, you use the concept that e to the a plus b is just equal to e times e raised to the a times e raised to the b, which is equivalent to that. But this one can be expressed in this manner. And this one can be expressed in this manner. So when t1 is 0 here, and here when t2 is 0. But if you look at this is the moment generating function because this is simplified as the moment generating function of y at t1. So 0 ni siya. And this is the moment generating function of y when t1 is 0 here. So in this proof, we have shown that if y1 and y2 are independent, then the moment generating function of y can be expressed as the product of its moment generating function. So actually, this one is actually the moment generating function of y1 at t1 or at t in general times the moment generating function of y2 at t. Okay, this one. Next, suppose that you can factor your moment generating function in this manner. This is assume Q, and you want to show that it is P, or you can write it in this manner. Kana. Another way of writing these terms. Okay, so here we will use lemma. What lemma is that? We will use this lemma, this one, lemma 3.3. So if x and y have the same moment generating function, then they have the same distribution. So what we are doing here is we assume that there exists two random variables x1 and x2, which are independent random vectors, such that each of them has the same marginal density as y1. So if they have the same marginal density as y1, yi's, then the moment generating function of x1 will be equal to the moment generating function of y1. And the moment generating function of x2 will have the same moment generating function of y2. Since we assume that they are independent, then you can write the moment generating function of x1 and y1 as the product of the two. And then, since they are equal from here, but joining this, since y is just a partition of y1 and y2, you have that the moment generating function of x is just equal to the moment generating function of y. So that using lemma 3.3, they have distribution, and since x1 and x2 are independent, then it follows that y1 and y2 will also be independent. So the essence of this lemma is that when two random variables are independent, then you can write the moment generating function as the product of its marginals. So this can also be written as the moment generating of y1 at t times the moment generating function of y2 at t. But the t here is actually at 0 t2 because t1 will be 0 and the t here will be at t1 0. Okay. So let's proceed and study more about the non-negative definite matrices. Non-negative definite, a function is non-negative definite if you can, this is the notation. No? So this is not read in terms of matrices. This is not read that u is greater than or equal to 0. Mathematically, inaana na siya, greater than or equal to 0. But in English terminology, what this notation is telling you is that U is non-negative, is a non-negative definite matrix. Now, the covariance of your random vector y is always a non-negative definite matrix. And this becomes a positive definite matrix if your y will have a continuous density function. Okay? So if your y has a continuous density function, then the covariance of y will become a positive definite matrix. So you want this characteristic because we want, if we denote covariance of y to be equal to sigma, we want sigma inverse to exist, no? So this lemma tells you some properties uh, of your non-negative definite matrix. So if a matrix is non-negative definite, then there always exists V, a unique V such that the U can be expressed as B square. So ibig sabihin, what this lemma is telling you na V can be expressed as the square root of your non-negative matrix U, no? So pwede nimo kuha square root. And if your U is positive definite, then your V is also positive definite. If U is positive definite, then U is invertible and the inverse exists. So mao man ni ang nice property of a positive definite matrix, because it becomes an invertible matrix and the inverse exists, and that inverse is also positive definite. Kung non-negative definite lang siya, invertible lang si U kung strictly positive definite siya. So when it is non-negative positive matrix, non-negative definite matrix, walay assurance na naa ang inverse, not until U becomes a positive definite. And another transformation that you can do for non-negative definite matrix having a rank R, so this is a square matrix having a rank R, you can always express U for a given matrix C, P by R, such that so you can always find a matrix C such that of rank R pod, such that you can express U as C prime, no? C prime. So C prime, C is P by R. This is R by P, so this is conformable. What you will get is a P by P because your U is a P by P. So that's why it's C prime. If this is P by P, this should be also P by P. So to make that P by P, it is C prime, no? So for any non-negative definite matrix, there always exists a matrix C such that U can be written as C prime. And if you have a matrix X n by P of rank R, then X prime X is non-positive, a non-negative definite matrix. But if R is exactly equal to P, ibig sabihin if the rank is exactly equal to the minimum of N and P. So pili lang nato si P. So kung ang number of linearly independent columns is equal to the rank of X, then X prime X becomes a positive definite matrix so that X prime X is invertible and X prime X inverse exists. So dapat ma-attaining rank R, no? So if the number of linearly independent columns will be equal to the rank, then X prime X becomes invertible and x prime x inverse will exist. So this is telling us that x prime x inverse, so x prime x is positive definite, so x prime x inverse exists. But the condition is if the number of linearly independent column will be equal to its rank, then this is true. Okay. Okay, definition. If your matrix is a non-negative definite matrix, we can define the square root because if it is non-negative, ingon to ganina sa lemma, na kay makit-an na B na unique such that you can write it U equal to B square. So that if you can write A into a B square, non-negative lang, so you can define the square root of a matrix or A raised to the 1/2. So next are some properties of a positive definite matrices. So A is assumed to be positive definite. So if it is positive definite, the inverse is also positive definite. You can swap the operations of inverse and its square root. Since it's positive definite, the inverse exists, so that this product of matrices here are just the identity matrix because the inverse exists. The transpose is just equal to that. And this is the determinant, no? So the determinant of the inverse of the square root of A, because you can write this as A inverse and then get the square root, is just equal to the determinant of that is just equal to the determinant of A and then get the inverse, and then you can also get the square root. Okay, so that is equivalent. Okay, next. This concept, Mahalanobis distance, is usually used when we try to compute the risk or the error committed by using the estimator. So here, the estimator is denoted by D and the parameter is denoted by U. So when we say error, we are looking at how different is your estimator from your parameter. Or in other words, pwede po ka kung ang imong estimator X bar, because this is a generic, dili raman pirmi X bar ang imong estimator for your parameter mu. You can use the minimum, the maximum, or the sum, no? So in particular, X bar to be a estimator for mu. So the error is the difference between X bar and mu. The risk will be the expectation of your error, the expectation of X bar from you, no? So usually, this difference is generally expressed in terms of distance or how far will be X bar from you. So in general, we call it Mahalanobis distance. This is an author, no? So he's the one who introduced about the concept of distances in terms of L. L here is usually referred to as the loss function, no? In terms of a loss function. So later you will see that the Mahalanobis loss function. So let's define what is the Mahalanobis distance between D and U, which is defined as the square root of a loss function. The loss function is denoted by this. So this is a loss function. So usually, unsay formula sa distance. So kung na ako'y A, B, C din Unsa gani ang formula ani? So kung na ako'y duha ka point din Oh, sige. I-ano na lang nato, two-dimensional. So if you have X and Y din na ako'y duha ka point. Say, let me call this X1, Y1. So mo ni imong X1. Mo ni imong Y1. And then this one is X2, Y2. So what's the distance of this point? The distance is equal to X1 minus X2 squared plus Y2 minus Y1 squared, di ba? Correct?
Yes, ma'am.
Okay. So, in terms of vector, unsa man ni? Di ba square norm na siya sa X1 minus X2, or kung vector na siya, that is the difference prime times prime and then plus this is the square norm of Y1. So kung i-change na nato vector. So in terms of vector, in general, mura na siya summation sa V prime U. No? Okay, so makita na ninyo na D minus U prime and D minus, duwara man ni siya. So in general, kung n-dimensional na siya, it's the sum, the square root of the sum, because this is V prime U. Kung na kay vector, this is actually your square norm of V and U, no? Or inner product. So kung wala na kay square, mo nang na-square root. Okay? So the length of the vectors, distances. So you have, so actually, ito ra ni siya. The norm of D and U. Okay, paon man nato ang square root. Okay, kaya ang square norm D minus U mu wala square root ana. So when it is wala nang square diha, that is the square root. And this is divided by sigma squared to make it normalized or standardized, no? So usually inanay man nag-itsura mura siya D minus mu norm over gi-standardized nimo by the variance. So gi-normalize nimo siya. Okay. Raised to the negative 1 na siya. Okay, so that is your Mahalanobis distance. And since you divided it by the standard deviation, the Mahalanobis distance is unit free. So this is the division there is to make your distance standardized. Okay, so the loss function is denoted by this symbol. It's called the Mahalanobis distance loss function. Actually, there are many loss functions, but for the following reasons, why Mahalanobis loss function is often used is because of ease of computation. Say, unlike if you have a loss function which is just the difference between D and U without standardizing it. Mas sayon daw kung imong i-standardize kaysa just getting the difference. Next, because of its invariance property. So the Mahalanobis loss function, that is, even if you do some transformation on your estimator, no, the loss function is just equal to the original estimator. So for example, kung naka-estimator na x bar, manana siya associated na loss function niya x bar with some parameter, say mu and sigma squared. Kung maghimo tag transformation din for example, mag-multiply ka ani og 2 plus any constant, say 5, ang loss function associated ani kanang 2x bar plus 5, of course mausab man ang imuhang parameter dinhi. Sana may parameter ani. Unsay parameter ani kung mag 2x bar ko plus 5? Unsa ang iyang corresponding mu? Unsay associated parameter ani? Nag-solve naman ta ani. Kanang maghimo mo transformation sa imuhang random variable. For example, y, naanay siya kaugalingong parameter. So kung maghimo ko sa ay plus b, unsa may iyang kaugalingong parameter? Di ba nag-solve naman ta ana dinhi? Oo. Una ako'y transformation. Una ako'y x man ako i-transform. Unsa man iyang mean? Di ba? Oh. So base anang gidiscuss nato last time. Unsay parameter ani? Oh, na ako'y y. Ang iyang parameter kay mu og sigma squared. I-transform na ako si y og x. Ay plus b. Mao man ni nahitabo. Na ako'y x bar. Iyang parameter. Mu og sigma squared. Man akong i-transform og 2x bar plus 5. So ang 2x x bar plus 5, unsa may parameter? Unsa iyang mu? Corresponding ani. Uy, paningog mo.
2 mu plus 5 mo.
Ha? 2 mu plus 5.
Yes, ma'am.
Okay, ang iyang corresponding sigma square. Hindi na to ganina, no? LJ,
Yes, ma'am.
unsay answer ani? Unsay ang corresponding sigma square? LJ. Wala si LJ. Kim. Natug man siguro ni ako estudyante. Naggato naman ta class, nag-discuss man ta o kini. Unsaon man ninyo paggamit? Kini. Mao may na transformation, no? So unsa may corresponding? Na ako'y x, mura ang itsura ato kay na ako'y x na mu sigma square. Mana akong x, akong gi x bar. Ang akong x bar gi 2x plus b na ko or plus 5. O man na transformation. So 2x bar. So, unsa may equivalent ani? Nara o kini. 2x bar plus 5. So, unsa man ni equivalent? O, correct na si Dina. May mo siyang 2 mu plus 5. So, unsa may equivalent sa ano? Kining A sigma A prime. Kim, LJ, Marivic, Inyola, Noli, Kali, Ryan.
4 sigma
Anybody?
squared, ma'am.
Ha?
4 sigma squared.
4
4 times
sigma
variance.
squared. No? Kinsa to?
Di na, ma'am.
Oh, may pasdin na. Bisan wa gitawag kay nitingog. Okay? Paningog pud mo ay mura man inyo ang mga gihuna-huna ba isulti, bahala grong isulti para makoreksyonan kaysa sige ra ko istorya dinhi manawag ko ninyo. Di mo maningog mura mag nagstorya kog screen na wala ko estudyante. Okay? Isapot na ko. Ngundang ta. So, ako ning tiwason, remark 3.2. So, ang advantage da aning invariance is bisan pa maghimo mo transformation sa imong x, ang loss function mo balik siya sa original na loss function sa imong y, no, sa imong original estimator. So that is invariance property. And if your sigma is positive definite, then we can always define a distribution of the random variable by a density function. But if your covariance matrix is non-negative definite, what we can do is to describe the distribution using moment generating function. So since we are not assured of a positive definite covariance, kaya dili ta sure kung naagi siya density function, that's why we usually solve some properties of your distribution using the moment generating function, because what is known is we are sure that it's non-negative definite. So to check some properties of the distribution, we use the concept of moment generating function. Okay, so the next topic will be focusing on normal distribution. So we will focus on the moment generating function of the normal distribution. But I don't want to talk. Next meeting na siya. Okay. Itaas na akong presyon. I will continue next meeting. Paningog lagi mo kay dili pwede na pangutanon mo man wala mo isulti sa inyong idea bisan unsa na inyong gihuna-huna. Stop recording, Shera. Shera, stop recording.